All right, so what we're looking at today is called parametric equations. Parametric differentiation. Okay, and basically for parametric differentiation, there's an assumption that we do the conic standard and we know what parametric equations are, which we don't, so we don't. So I'm going to explain very briefly what they are, but what we do need to be able to do is differentiate using parametric equations. It's really easy, usually merit and a quick find a gradient or find a tangent or an equation of a tangent or whatever, okay? So basically what happens with parametric equations is that you get two equations, one for x and one for y, but in terms of a different variable, usually t. And the idea is that x and y are not reliant on each other, but on the t. So if you put a constant in for t, so let's say we had some straight line, we wanted to try and get a straight line, and we had, just going to jiggle over here for a minute, don't write this down, oh, it's not worth it. All right, something like that. Let's put a square in there just for fun. All right, so what we would do to find out what this looks like, this is just a Cartesian graph, just an x, y graph. What we would do is we grab our axis and we go, okay, what's the answer when t equals 1? 2 for y and 2 for x. So that point there is on the graph. What's the answer when t equals 0? 0 and 1. So 0 for y and 1 for x. So this point's on the graph. All right. What's the when t equals -3? We get -6. -3 squared is 9 plus 1 is 10. So we've got 10 for x and -6 for y. Way down here. Oh, yeah. So this is not a straight line. This is actually a quadratic. All right. It's just a quadratic that goes like this. But we actually don't need to know that. All right. We don't care what it looks like. What we need to know is how this behaves. So we put in numbers for t, any number we like, we will get a point, an x and a y point on that graph. Okay? So given that we have equations like this, we can actually just treat them as though they're any line. But what we have to do is differentiate them supposedly parametrically. All right? Parametric equations, parametric differentiation. And what we do is instead of differentiating dy by the x coordinate, dx, we do it by t. So we're going to differentiate some equation mentioning t. I don't know why I'm writing it y then x each time, just for confusion. Doesn't make any difference. Maybe we will swap those over so we don't get quite so confused. I do know why, but I'm not going to tell you just at the moment. So we get these things according to t, and then we differentiate each one. So we have a dx by dt, and we have a dy by dt. Now we're trying to find the gradient, or we're trying to differentiate to get dy by dx. We want dy by dx. All right? But we've got these two things. So we want dy on the top, which is why I do y first. But we want x on the bottom, so yeah, we multiply by the reciprocal so that we can cancel these out. All right? So in multiplying by the reciprocal, what's that the same as? Dividing. So in effect, what we can do is divide by dx by dt. And that will give us the answer. All right, so let's have a look at an example. We could have done that one actually, silly me, but never mind. Let's do that one. E.g., x equals t squared plus 1, y equals 2t. So dx by dt equals 2t, and dy by dt And this is why this particular notation I've been saying is really good, because once we get into other variables, it tells us what we're doing. The x line differentiated by all the t's in it, and the y line differentiated by all the t's in it is 2. So dy by dx equals this one, which is why I do it first, divided by that one. So 2 over 2t, or 1 over t. That's the gradient function. All right? If we were wanting to find out what a coordinate on the graph was at a particular time, so at t, we could put x t equals lambda 2, so x equals 4 plus 1 is 5, and y equals 4, so 5, 4 is the point where t equals 2, all right? The gradient at that point, dy by dx, will equal a half, 1 over t, which is 2. So that goes in 3 places, one in to find x, one in to find y, and usually in to find the gradient as well. All right? And then we just put it all together in our normal way. But if we're running after the gradient, that would be it. Okay, so normally when they do these ones, they actually use trig. So I'm going to have a look at a trig one. So I wrote one out so that I didn't get lost. So if x equals 2 cos 2t and y equals tan squared t, find the gradient, find the equation of the tangent at t equals pi by 4. All right, Rachel. 1 over 2. All right, we put t in 3 places. 1 for x, 1 for y, 1 for dy by dx. Okay, so we've got this question here. So we want to go through it and we want to differentiate x first. So in this case, I'm just going to tidy it up a little bit. All right, so both of them using the chain rule. So this one, 2 is a constant. This differentiates to negative sign, then differentiate the 2t to give 2. Okay, this one, take the 2 to be a power. So take the power, multiply by it, decrease the power by 1, and then multiply by what's inside. So we've got those 2 as our dx by dy. And they look really awful, but they're actually, who cares? It doesn't matter what they look like, as long as they're right. All right, so we need to find at t equals pi by 4 that x equals 2 cos 2 pi by 4. Remember to put your calculator into radians, and that gives us, and I've already done it, that gives us 0. And when y equals tan squared pi by 4, remember we will put tan pi by 4 squared when we do it, and that gives us 1. All right. When we put these two together to get the gradient, dy by dx equals 2 tan t sec squared t over negative 4 sine 2t, and at pi by 4, that equals, this thing here it comes out to equaling negative 1. You can have a go at that later and make sure that you can put it in your calculator to get that as the answer. So we've got a gradient of negative 1 and the point 1 and 0. So we've got y minus 1 equals negative 1, x minus 0, or y equals negative x plus 1 as our equation of the normal. All right? Now, just one more thing. Peter. I meant the equation of the tangent because that's what we're asked to find. What will we do to get the equation of the normal?
We would reciprocate this.
We would reciprocate and
Multiply by
negative. Okay? So it'll be negative 1 over negative 1, which would be 1.
For the last before, sorry. Yeah. Were you finding the gradient function when t is equal to 2? Is that what you're saying?
I was finding the gradient when t equals 2.
Yeah, so you the question, so that'll be part of the question, find the gradient function when t equals 2.
Yeah.
Okay,
I was just showing you how you find x and y. You wouldn't need to do that part because you're not finding the equation.
No.
So if you're just finding the gradient, you'd just find that part. Now the last bit is that all functions can be derived again and again and again. So it's handy to know what the second derivative test is for this. Now they haven't actually asked this for a long time, but it is on your equation sheet. It is on your formula sheet. And what it equals is weird. So I'm just going to go through what it is in case they ever do ask you.
Is this entirely different to the parametrics, or is it?
No, this is a second derivative using parametric equations. Okay. So we already know that we've had, so this is the notation for a second derivative. And what that says is dy all squared by the x squared. So it's a weird sort of a notation, but that is the one that they use. And what it's equal to is you've already found this, right, down here somewhere like this. Right. And you have to differentiate it. Okay, so that bit there says whatever you found for the first derivative, differentiate it with respect to t again. It's already in terms of t, so this one would be t to the negative 1 over t to t squared, right? So if we were doing this one, it would be dy by dx equals 1 over t. So d by dt of dy by dx, or do it again, differentiate this, it would equal negative t to the negative 2. All right, so that's that bit. You've already found this too. So you're going to divide by it. Same as you did before. So when we were dividing, it's the same thing. So altogether, you've got negative t to the negative 2 divided by dx by dt, which in this case was 2t. That would be the second derivative.
Right, yeah,
Right?
that makes total sense.
No, and it's not supposed to, and it is pretty yicky, but it will become a little bit clearer once you've practiced it. All right, so that's parametric differentiation for you. It's usually in the paper at least once, sometimes twice, and it's normally something that's reasonably easy to do because all you're doing is differentiating each one, dividing the y one by the x one and substituting something. All right, so it could be in there as a rate of change, it could be in there as a gradient function, could be in there as a find the gradient of the normal or an equation of a line, but it's as easy as that, which doesn't seem easy now, but will. Definitely is easier than other things. All righty, press stop.